Well, good morning, and this is another video that I've done this morning. I went down and I was trying to observe Walney Lighthouse at night time whilst it was still dark. And what do you know? Of course, we see Walney Lighthouse from a distance of 13.25 miles away, and the height was just 2 feet. Now then, it's important to get some calculations done here, because in the globe model we have a sphere and we have water, being acted upon by the Earth's gravitational pull, which turns the globe into a globe. That's what it does. It makes water curve. Now obviously we have a calculation for that. It's 7.98 inches per mile squared. Now that is a calculation that has to work on water. It has to, in order to get the size of the Earth that we are told that we live on. Now let's put those details into a curve calculator. So looking across water, which is being acted upon by gravity, pulling it at 7.98 inches per mile squared around and around and around, what we get is a hidden geometric of 88 feet, and including refraction, which we all know is nonsense, 74 feet. Now then, what is the height of Walney Lighthouse? Well, Walney Lighthouse has a focal height of 70 feet according to the Lighthouses of Northwest England, and by Wikipedia 69 feet. Now that's 69 feet above mean sea level, so that is the central point over the entire year of what the height would be. So for instance, if you had a tide height of 4 meters at low tide and 6 meters at high tide, the mean sea level would be in the middle point of that, so 5 meters. Now in this location where I live, we have a tidal change generally between 1 meter and 8 meters. Occasionally you get it up to 9 meters, and occasionally it goes down to 0.3 or 0.2 even. But in general it's between 1 meter and 8 meters. So that would put the mean sea level around about 4.5 meters for this location. So that's interesting to note, because today when I went down to do the filming, what we have, this is Thursday the 5th of December, and if we go to essentially 7 o'clock, 6:56, it's the nearest I can actually get to the time that I was filming, we get 5.89 meters, so that was the height of the tide. Now that is higher than mean sea level, which means that we have to account for that by subtracting the additional height of the tide at that time from the focal height of Walney Lighthouse to be accurate. So we're looking at 1.3 meters or thereabouts, let's say 4 feet. So we're going to take 4 feet off the focal height of Walney Lighthouse. So we're looking roughly between 65 and 66 feet above actual sea level was the height of Walney Lighthouse when I was filming it this morning. One other thing I would like to talk about today was the very strong winds that you'll see in the, well, you won't see the winds, but you'll probably hear the winds in the video, and you'll certainly see the chop and the how high these waves were today. Now this is for today. This is the forecast. Obviously, we're looking 2 to 3 feet strong chop. That's wind-driven waves. And we also have a swell. So swell is completely different. That's something that's storms that happen a long way away, hundreds if not thousands of miles away, causes a swell eventually to arrive in this location, in all locations throughout the world really. Everywhere has swell for the most part. In this particular case today we're looking at swell of between, well, swell 3.5 feet every 5 seconds. and we're looking at 2 to 3 feet of wind-driven waves on top of the primary swell. So if you look at this graph over here and you see this is let's say this is the swell, so that is the primary swell, 3.5 feet, and above that you'd have the wind-driven waves too. So we're looking at 3.5 feet and 2 to 3 feet. So all this is blockage. Now I'm trying to film from 2 feet. So essentially I am lower than the peaks of these waves. That's also something interesting to take into account. Now, without further ado, I shall show you the footage that I captured this morning. And, well, before we go there, if we see Walney Lighthouse, that means that it doesn't conform to the 7.98 inches per mile squared. It doesn't conform to that. What does that mean? Does that mean that we don't live on a globe? No. It means that what we are viewing in the globe model is a hologram. In fact, everything that you see below 7.98 inches per mile squared on a calculation, if you ever see that over water, ever, it is always a hologram. It isn't really there. Think about that. It doesn't matter if it's just a few feet of something that you're seeing, or it doesn't matter if it's a mile further away than it should be, because as soon as that calculation is broken, the moment that calculation does not work, the moment that this globe model over here, this thing isn't real. That's essentially the whole point. Nothing works. No battleships, no submarines, they wouldn't work if this calculation fails. 7.98 inches per mile squared. This body of water that you're looking at here on this, what would you call it, model, this 7.98 inches per mile squared, this water has to be bending at that rate. It cannot be anything other than 7.98 inches per mile squared. It can't be. It has to be to make this model work. The moment you see something further than you should, the moment the globe model turns it into a hologram. Let that sink in. It doesn't have to be incredible distances. It doesn't have to be 100-mile observation, 50-mile observation. The moment you see further than you should, it automatically becomes a hologram. Let me play the video. So this is Devonshire Dock Hall in the morning. This is off the railings at BLO 97 today, so about 70 metres nearer than the BLO 98 that I filmed from before. I'm trying to focus on this lighthouse today. There we go. So right now I'm about, I would say 40 feet or so above actual sea level. So what I'm going to do is go down and film from the bottom of the steps, because that is exactly where the tide is. I'm going to move because I'm going to get wet. Right, we saw the lighthouse there. If I get right down, so I'm approximately 4 feet above actual sea level here, so let's go down as low as I can. So we're going to go down to 1 foot. Now those waves have got pretty high. Crazy. Whatever's happening over there, those breakers are actually higher than what we're trying to focus on. But I can certainly see the lighthouse above them with my naked eye. So there, we saw it there. So maybe if I go to 2 feet instead of 1, we might be able to get over those breakers. Would help if I pointed it in the right direction, I suppose. There we go. Hey, we saw it. Hey, we saw it. That was really weird. I was focusing on the water, but the lens was so far out that the wind, because it is howling, the wind was blowing, and it was blowing my camera to the right. So when I thought I was holding the camera absolutely in a direct line of where I thought the lighthouse was, in effect, the long lens was catching the wind and dragging me to the right. So we got it eventually from 2 feet, which is pretty awesome actually. I'll need to do the calculations on that, but I will actually show you where I am. Ooh, it's cold as well. Wasn't it interesting though, the height of these waves, these massive waves. I say massive waves, but substantial enough, 5-6 feet maybe, easily obscuring stuff in the background. But so hello 97. Whew. And it isn't half murky over there, I tell you that. Even though the camera's sort of much brighter. But you got a very good visual then of how those waves were able to hide things. In actual fact, I'm just going to say it, guys. Earth curvature isn't Earth curvature. It's water movement, ocean movement. That's all it is. It's the movement of the water in with different types of effect. Different effects, shoaling, tide movements, shock, swell, all of that. And probably some of the things that I've not really considered. But that's all it is. That's what gives you the pressure build-up of the water as it's moving, creating locations where you get these effects that actually increase the height of water. That's all it is. It's nothing to do with the curvature of Earth at all. Nothing whatsoever. We see far further than we should, and well, anyway, and this is the point, that every time you see a single mile further than you should, immediately the object that you're looking at becomes a hologram, because it's not really there. The second that you see something that's further than it should be, it isn't really there. So ask yourself, how do submarines work? And you're able to attack other boats. How do boats ship to ship when they're fighting? How do they do that? If they see a ship 15 miles away and it's not really there, what do they have to do? Do they have to wait until the curve calculator says it's okay for them to attack, so that they're not shooting at a mirage? Think about it. Every single time you see an observation that defies the globe model, no matter how big or how small, it is always a hologram. Think about it. Think about it. I'm going to leave you with that because it's absolutely bitter. And yeah, I'll see you all in the next one.